Assalamualaikum warahmatullahi wabarakatuh to my fellow panel. I hope everyone is doing well and safe during this unprecedented time. My name is Muhammad Shafiq bin Abdul Hadi and I am under supervision of Dr. Muhammad Shukri bin Hadi. In this video, I will be presenting about my research in active vibration control of horizontal plate structure based on Bacterial foraging optimization. I will be explaining about the introduction of this research, problem statement, the objective and scope of study, methodology, result and discussion, lastly, conclusion and recommendation. For your information, there are various advantages of the flexible plate structure, which is lightweight, low energy consumption, safer operation, and reduced maintenance costs. Therefore, many industries use flexible plate structure rather than rigid structure. The flexible plate structure are mainly used in engineering applications such as solar panel, bridge deck, satellite plate, and electronic circuit board design. However, when subjected to the force of disturbance, the flexible plate structure are affected by unwanted vibration. The stability and effectiveness of the system will be affected. The unwanted vibration can lead to noise, fatigue, wear and damage. So that the model system must be modeled to attenuate the unwanted vibration of the flexible structure. As we know, excessive vibration can lead to noise, fatigue, wear, failure, and ultimately reduce the efficiency of the flexible plate structure. The example of attention-grabbing incident due to resonance was occurred in 2019, when Norfolk Bridge, Taiwan, collapsed due to typhoon strong winds and heavy rain. It can be seen that the vibration control is vitally important. In addition, the unwanted vibration needs to effectively suppress from the system. Exaggerated vibration might affect the stability and performance of the system. Based on previous studies, active vibration control had been applied by the researchers as a way to control the undesirable vibration. Active vibration control can overcome the limitation of the passive vibration control. Moreover, active vibration control provides simple maintenance, high efficiency, and inexpensive compared to the passive vibration control. There are two objectives of this study. Firstly, to model the horizontal flexible plate system using least square and Bacterial foraging optimization, and secondly, to simulate a proportional integral derivative controller for vibration suppression in a horizontal flexible plate structure. Scope of study of this research are modeling the horizontal flexible plate system based on least square algorithm and Bacterial foraging optimization algorithm. Then, the model will be validated by using mean square error, post-zero diagram stability, and correlation test. The Bacterial foraging optimization objective function is limited to single objective function based on lowest mean square error. The development of PID controller by active vibration control technique and tune using heuristic method. The controller will be validated by using single and multiple sinusoidal disturbance. In this study, there are two objectives to achieve the study, which is modeling the horizontal flexible plate structure based on least square and Bacterial foraging optimization algorithm. Then, the model will be validated using mean square error, post-zero diagram, stability, and correlation test. Based on comparative assessment, the best model will be selected. Therefore, research number 1 is achieved. Next, based on best model selected, the model PID controller is developed. Developed PID controller will be validated using single and multiple sinusoidal. Once developed model validated, objective number 2 is achieved. Next, I will talk about result and discussion for modeling via least square algorithm and via bacterial foraging optimization algorithm, then comparative performance between least square and bacterial foraging optimization algorithm. Then I will talk about the PID controller development, and the PID controller is tuned by using heuristic method and the controller validation. Heuristic method was applied in this study. It is problem-solving approach with flexibility to produce satisfactory solution when involving complex data. The tuning parameter involved in least square algorithm was model order only. Therefore, heuristic method of tuning was applied by increasing the model order with increment of 2 and stopped at 18. This larger model results with larger mean square error, which is not favorable. Table 1 shows the set of parameters used to achieve the best model using least square algorithm. The best model order is 16 and the number of parameters is 32, and they are discrete time transfer function for the least square algorithm. Figures 1 and 2 shows the actual and least square modeling outputs in time and frequency domains. The developed model efficiency can be accessed by observing time and frequency domains response of least square modeling overlapping with the actual response that was measured experimentally. It is essential to overlap to ensure an accurate representation of the horizontal plate structure. The purpose of the dotted lines seen in Figure 1 is to distinguish training and testing data, where 2500 for training data and 2500 for testing data. Then, Figure 3 shows the normalized error of the output between actual and least square modeling on the distinction between measured and predicted data. One of the correlation tests in Figure 4, which is autocorrelation test, is within 95% confidence level, which indicates the degree of similarity in developed model and actual data are alike. However, the cross-correlation in Figure 5 resulted with bias, where it does not pass the percentage of confidence level. When the correlation is low, it shows no relation between the two variables. This model has a good stability since the position of all poles are located inside the circle in the pole 0 diagram as illustrated in Figure 6. Tuning parameters involved in modeling via bacterial foraging optimization are model order, number of bacteria in the colony, number of cumulative steps, the run length unit or step size, and maximum iteration. Table 2 shows the set of parameters used to achieve best model using bacterial foraging optimization algorithm. Model order is 10, number of bacteria in the colony 50, number of cumulative steps 30, the run length unit or the step size is 0.004, the maximum iteration is 50, and this is the discrete time transfer function for bacterial foraging optimization algorithm. Figure 7 shows the convergence of the bacterial foraging optimization algorithm. Figures 8 and 9 shows the actual and bacterial foraging optimization modeling outputs in time and frequency domains. The time and frequency domains response of bacterial foraging optimization modeling overlapping with the actual response that was measured experimentally. It is essential to overlap to ensure an accurate representation of the horizontal plate structure. The purpose of the dotted line seen in Figure 8 is same with the least square algorithm, which is for testing and training data, 2500 for training data and 2500 for testing data. Figure 10 shows the normalized error of the output between actual and bacterial foraging optimization modeling and the distinction between measured and predicted data. Figure 11 shows that the autocorrelation of the bacterial foraging optimization algorithm is within 95% confidence level, which indicates that the degree of similarity between developed model and actual data are alike. However, the cross-correlation in figure 12 resulted with bias, where it does not ask the percentage of confidence level. When the correlation is low, it shows no relation between the two variables. This model has a good stability, since the position of all poles are located inside the circle. Comparative results in between least square and bacterial foraging optimization were summarized in Table 3. This comparative is made to select the best model to represent the flexible plate system in the active vibration control system. Based on Table 3, the minimum mean square error for least square is 3.3989 times 10 power of negative 4, and for bacterial foraging optimization is 4.1379 times 10 power of negative 4. As recorded, the mean square error, at least for least square algorithm, was slightly lower than the bacterial foraging optimization algorithm. Next, the developed models is validated by stability of pole zero diagram. According to the result obtained, the validation for least square and bacterial foraging optimization were considered stable because every pole managed within the pole area. The last validation is correlation test. The models need to correlate within 95% of the confidence level. According to the result obtained, most developed models are within 95% of the confidence level in autocorrelation test, but biased in cross-correlation test. Next, the model order of the bacterial foraging optimization algorithm is smaller than the least square algorithm, which is 10 rather than 16. This will make bacterial foraging optimization considered the best model compared to the least square algorithm. According to the previous researchers, Billings 2013 had recommended that using the simplest model to represent the actual system. After we select the best model to represent the flexible plate system, the PID controller is developed. The transfer function of a best model, which is bacterial foraging optimization algorithm, is put in here, and then the proportional integral derivative gains tuned using heuristic method, and then single sinusoidal disturbance, and then this is the reference input. Next, figure 15 shows that the simulating block diagram of PID controller for multiple sinusoidal. It is the same with the previous slide, but the difference is that we are using multiple sinusoidal disturbance in this simulating block diagram. PID controller is developed from the transfer function obtained in modeling to suppress the vibration on the flexible plate system. Heuristic method is used to obtain the best parameters of the PID controller. The three parameters of the PID controller are proportional gain, integral gain, and derivative gain. With PID controller, proportional gain is used to lead the system to the set point, and then the integral gain will deal with the steady state error, and derivative gain is applied to the lessened overshoot in the system. Table 4 shows that the best PID parameters obtained based on heuristic method. For the proportional gain 0.8, for the integral gain 0.2, and for the derivative gain is 0.001, and attenuation level is 5.2. Figures 16 and 17 shows the performance of the PID controller under single sinusoidal disturbance in time and frequency domain. The result obtained shows that the PID controller successfully suppressed the decibel magnitude at first mode vibration at 57.51 to 52.31. The PID controller recorded the highest attenuation level by achieving 5.2, which is equivalent to 9.04%, as listed at table 5. Then, the multiple sinusoidal was applied to the developed PID controller in order to assess the robustness of the controller. Figures 18 and 19 illustrate the performance of the PID controller at the multiple sinusoidal disturbance in time and frequency domains. Based on the result obtained, the PID controller successfully attenuated 5.2 in the first mode vibration. The decibel magnitude of the system is reduced from 63.53 to 58.33, which is equivalent to 11%, as illustrated in the table 6. This shows that the use of the developed PID controller effectively suppresses unnecessary vibration of the horizontal flexible plate system. In conclusion, the flexible plate system was properly modeled using least square algorithm and bacterial frogging optimization algorithm. Next, the best model to simulate the dynamic system is made on the basis of minimal mean square error, high stability, and good correlation test. Then, the PID controller was designed and simulated based on active vibration control with the intention of dampening the unwanted dynamic response generated by the system. Lastly, the horizontal flexible plate system effectively suppresses unnecessary vibration. For the recommendation, the modified bacterial frogging optimization algorithm can be introduced. When the improved algorithm is used to model the structure, the possibility of rapid convergence of the model system, low mean square error, and high precision will increase. Next, an algorithm-based tuning controller such as the bacterial frogging optimization of PID controller can be considered to minimize unnecessary vibrations generated in the horizontal flexible plate system. A comparative study between PID and bacterial frogging optimization of PID can also be performed. If you have any inquiries, do not hesitate to contact me. That's all from me. Thank you.